Today we're going to take a look at section 2.1, which is measures of change over an interval. It's going to be a lot of language, okay? So we're going to be doing a lot of interpreting, writing things out in sentences, figuring out what we have. We're going to use the calculator a little bit, but it's not heavy calculator kind of stuff today. It's big in terms of interpretation, okay? So we're going to take a look first at three different formulas, I guess we'll call them. The first one is the formula for change. The formula for the change is found by taking f of b minus f of a. One way to think about this is to take the newer or the more recent value minus the older value. New value minus old value. And the value today minus the value 3 days ago. So if you're trying to lose weight, you take what you weigh now minus what you weighed 3 months ago, and that's the change in your weight. Okay? A percent change, we've seen this before. We didn't do a lot with it, but we saw it with exponential functions. This is that f of b minus f of a like we just had on change above, but then we divide by f of a and multiply by 100. Do you guys remember seeing that one?
Yes.
Yes. Like I said, we didn't do a lot with it when we did it, but we did talk about it in passing. And if you think about it in this sort of new versus old language, this is the new value minus the old value divided by the old value, and I'm going to scoot this over just a little bit, times 100. And the times by 100 gives you the value into a percent. That's all that's really doing. So that is percent change. We talked about that with exponentials because with an exponential function, the percent change is constant. So if you did it between 1998 and 1996, it would be the same thing as if you did it between 2002 and 2000, right? Okay. Average rate of change we've also talked about, and that's the same numerator, f of b minus f of a, but what we divide by is b minus a. We had a name for this. What was the other name you've seen for this?
Slope.
It's slope, right? This is slope. And again, this is a constant value for a particular kind of function. What function has a constant slope? Linear. Okay? So not all functions do, but linear functions do. And this gives you, and if you think about it, we've had another versions you've seen, y2 minus y1 over x2 minus x1. That was another version you've seen of this particular formula. They're all the same, just a little different notation. So we're going to be working with these three formulas, okay, and interpreting, that is writing a sentence of interpretation of what we have found. So we've talked about the formulas and how we calculate it. The next thing to talk about is how we describe the change. There are 4 components you'll write down every time you write a sentence describing change. You're going to specify when it's happening, okay, from 1990 to 1995, or from the beginning of when I'm thinking about the question I just graded, the buffet started, there was a reception in our questions in our homework or in our test, from the beginning of the reception until 2 hours later, okay, from January to August, whatever, that's change, the when part. What talks about the quantity changing? What is it that's changing? So the one that we did on the test, it was the number of rolls. They were changing. The example I give about the weight loss, it's the weight that's changing. Okay, so whatever it is that's changing is next. How? It's either increased or it's decreased. Okay? We had an increased, maybe your increased activity level, number of minutes of activity you're getting. Or maybe it's a decreased number of rolls. And then the number 4, it says by how much. That's the numerical value. How much has it really changed, including units? So it's decreased by 4.2 pounds per month, like a weight loss, right? Number of pounds per month. So there's always going to be a something per something else if you're describing the average rate of change. You're going to have a percent if you're describing a percent rate of change. Or you'll just have an output value if you're just describing change, like pounds. And it'll make sense when we actually put all 3 of them into play and what parts of them actually are different. Okay, and so we have an example. You guys ready for it? All right, so we're going to calculate the change, the percent change, and the average rate of change for the following, and we're going to write a sentence interpreting each one. So the first one is the number of internet users in China was in 1997 was 0.9 million, and in 2000 was 12 million. So we're going to calculate the 3 quantities first. So the first one we're going to calculate is change. So what are we going to do when we calculate change? The new value and the old value, right? What's the newer value here? The value in the year 2000, which is the 12 million, right? So it's not always a bigger number, but it's the one that's more recent. This would be our 12. We'll put units on the end. What was our earlier value? 0.9. And if we subtract these, what do we get? 11.1. And what are the units for that? Million users. Right, I'm going to calculate all three quantities first, and then we'll write the sentences. So let's calculate the second one. After change, we have percent change. And percent change is kind of cool because if you've already calculated change, then you know the numerator, right? It's the same numerator. And the same will be true for average rate of change. It's going to be the 11.1. If you don't want to write it that way and you want to write it all out, it's the 12 minus the 0.9. Either way. The denominator is the older value. In this case, that's the 0.9. And then we multiply by 100. So if you take 11.1, which is our numerator, grab your calculator, divide by 0.9, and then multiply by 100, what do you get? It's going to be a big number, just so you know.
1,232.3.
Yeah, and we'll go with the 3 decimals like we've been going with, unless we're told otherwise. So if it's 3 repeating, we'd have 3 threes. Okay, and then there's our percent. Okay, so that's the second one. It is just percent. The reason it's just percent is because if you take a look here, the numerator is in millions of users and the denominator is in millions of users, so the millions of users cancel out. Okay, so the only thing left is the percent that came across when we did 100% here. Okay, so average rate of change we're going to abbreviate to AROC. Okay, average rate of change. Because I don't want to write it all out, and you don't either. And later on we'll have another abbreviation for another rate of change. Numerator is the same, the 12 minus the 0.9. What's our denominator, though, for an average rate of change? Yeah, it's how the years are changing, and the newer year is actually the year 2000, and the older year is 1990, what was it? 7, fantastic. Okay, 1997. So my numerator is 11.1, my denominator is 3. So what is 11.1 divided by 3? 3.7, exactly?
Yes.
Fantastic. And then we can go back to what we divided to look at the units on this as well. The units on the numerator are million users, and the units on the denominator are years. So this is million users per year. Okay, so is everybody good on the calculations? Is everybody good on where we got the units for each of them? Okay, now here's the cool thing about what we're going to do next. Almost all of the 3 sentences are going to be exactly the same. The only part that's going to be different is the numerical value with units at the end. Okay? So in some sense, if you were working like I am on the iPad, you could copy-paste, right? I know, I wish there are times when I'm writing in pencil and I'm like, where's that copy-paste? Like, that's my nap, because I use the iPad so much to do this. It's like an automatic reaction, or the undo button. I like that one too. It doesn't work very well when you're writing with pencil, does it? It really doesn't work with pen. Okay, so we're going to find out, we're going to go in order. The first thing is to specify the interval. So what is the interval over which this change is happening? What is it? 1997 to 2000. Okay, so that's where we're going to start. From 1997 to 2000. And all 3 of the sentences we're about to write are going to start this way, exactly. from 1997 to 2000. The second component here says what? What's changing? Okay, we don't need the word millions, not necessarily. We're going to use it later. The number of users,
Per year.
not per year,
In China.
in China. What are they using? The internet. That's actually important, right? I mean, like, this isn't users of the toilet, right? We're users of what? Well, they're the users of the internet. Okay, so this is from 1997 to 2000. The number of internet users. And we are going to write the in China, just like you guys noted. That's what's changing, the number of internet users in China. Okay? Now, we need to decide whether they are, or how they're changing. Do they increase or did they decrease? And you can look at the values themselves to tell you, or you could look at the calculations that you made. If you look at the values themselves, you're just looking at, does the earlier one give you a smaller value or a bigger value than the second one, right? If you're looking at the quantities that you found, they should all have the same sign at the beginning of them. Positive means it's increased, and negative would mean it's decreased. So what's happened to our users in China? They've increased, right? So the number of users in China increased. And we will talk later about, and I've mentioned this in passing once before, we will talk later about when and how we change the phrasing here, but this is always a past tense. We had a starting time, we had a stopping time, so it's always in the past. So we'll always have the ed at the end of it. You're never going to write it with an ing. It happened already, it's in the past. Increased or decreased. And then the last thing we do is we do the by how much. So our first one here, in fact, before we do that, I'm going to cheat. Do you know what I'm going to do? That. I know. You don't have that feature on your paper. But if you did, you would use it, wouldn't you? Okay. So this is the statement. It'll be exactly the same for all three of my changes. And the last thing that will come will be what this value is with the units. So this one's going to say now 11 million users, 11.1 million users. This one's going to say 12.33.333%. And this one's going to say 3.7 million users per year. And that's the end of it. So I'm going to fill those in. So this one is 11.1 million users. The second one was 1,233.333%. And the last one that I've run out of space for, almost in the gray color that I have, is 3.7 million users per year. There's a structure, and that structure will be present in every single one of these changes that you interpret. All right, any questions on this one? Yes.
So on the homework, can we just put from 1997 to 2000 the number of internet users in China, and then put like a colon, and then put 3 colons in it?
Oh, you could like write them all three together?
Yeah,
You could do
increased by
that.
11 million, increased by...
Yeah, you could do that. There might be occasions that where it doesn't ask for all three. So make sure that if it only asks you for one, you're giving the one it asks for.
Okay.
But yeah, if you wanted to sort of like join them all together, that would be okay.
Okay.
Yeah, you could do that. That's a good question. Yeah. Okay, any other questions on this one? I know it's a little bit warm in here. Yeah? It's warmer next door.
Oh,
Just so you know. I haven't even been there today, and I'll guarantee it because I was there yesterday, and that room over there has really difficult time controlling the heat and the cooling. Sometimes we freeze in there. All right. Next one. Okay, we've got a table for this one. This one says a travel agent promoted a cruise to Alaska. Anybody want to go on a cruise to Alaska?
Yeah, I'm in.
That's where I want to go. Cruise to Alaska. In the summer when it's beautiful.
Yes, we did, and it's great for about 2 days, and then everything looks the exact same the rest of the time. There's like mountains, glaciers. We saw one there though.
A bear. That's great. All right, so this travel agent, she's doing some cruises to Alaska, and she's doing this over a course of several months. The following table shows her cumulative ticket sales after every 3 weeks. So this is going to be increasing the whole time because she's adding to it. So what we're actually looking at, for instance, is that in the first week she sold 71. But in the fourth week, that means during the first 4 weeks, she sold 197. Is everybody okay with that? So it's not saying in week 4 she sold 197. Cumulative words in there. All right, so the first question asks us, what is the change in the number of tickets sold between weeks 4 and 16? So we do need to be careful that we're using the data that it's asking us for, and it talks about week 4 and week 16. So this is the data that we're going to be using from the table. Okay? How do you calculate change? New minus old. So what's the newer value? 3,660 minus the older value, which is 197. And what do we get from that value? Excellent. And anytime we're dealing with context, which is almost all the time in this class, we're going to have the context solutions units as well. And that would be what in this one? Tickets. Yeah, you can put the sold if you want. Tickets are the units, so that's sufficient too. Did it ask me to interpret this? No. So don't do more work than the problem asks for, okay? That's all this problem asks for. We're ready for part B. Good? Now, part B says, what is the percent change in average rate of change over the same interval? So we're going to calculate the other two quantities that we've learned how to calculate over the same time interval from 4th week to the 16th week. So we'll do the percent change first. So our percent change is to take the same value that we just found. What was it? 30, I'll write it out. So we had 3660 minus 197. And what do I divide by? The earlier value, the 197. And then I do what? Multiply times 100. Okay, so take that value, divide by 197, multiply by 100. It's a large value again. What do you get? Thank you. Does everybody have that? All right, our last one is the average rate of change. Same numerator, 3660 minus 197. What's our denominator on this one?
4.
What is it?
4?
Not 4. 4 is in it. 16 minus 4. So it's the weeks in this one, right? It's the week that we're at. 16 was the later week, 4 was the earlier week. And if we subtract and do our divisions appropriately, what do we get? Thank you. 288, what was it?
0.58.
Was it exactly 0.58?
3.
3? It's okay, we'll do 3 decimals. What are our units for this one? Tickets sold, or if you want, you can do just the tickets per,
3 weeks.
no, per week, yeah. It's still weeks. Even though the table is only giving us the value after every 3 weeks, we still divide it by the number of weeks that it changed between week 4 and week 16, 12 weeks. So she's selling about 288 tickets per week. That's what we're finding out between that time frame anyway. And then it says to find an appropriate model for the data. So grab a calculator. This is the only one you're going to be using your calculator on for a data regression today. All right, there's no reason to do any alignments different than what they are because this is numbers of tickets or small values. It's not years or anything like that. Okay. Oh, I've got one entered wrong. Oh, I should show you this so that you can see this is why we look at it. Do you see what I looked at and I said, oh, I know I entered it wrong? Can you see it? I've got a stray dot down here and the data didn't really look like that. I entered something wrong, so I can go back and fix that now. That's it. Okay. So we have to decide what models are appropriate to try. So remember, the first thing we choose is we have to decide what's going on with the concavity. Is there a concavity change? Yes. And if there's a concavity change, we're limited to 2 models to try. What are they? Logistic and cubic. Okay, so those are the only options that we have. And we do need to try both of them, okay? Because one may fit the data really, really well and one may not. And it's hard to tell sometimes just looking at it and saying, oh my goodness, I know for sure and certain this is what's going to be. So we need to check both of them. And we will. So we're going to do stat calc. And we'll do logistic first because you guys saw that one first. Logistic. And put it into the Y1 of your calculator. Because our goal is to check and see if it fits. And if we don't graph it, we won't know if it fits, right? So I'm going to hit graph and we'll see what happens. Oh man. Hard to imagine anything would be a better fit than that, right? It looks pretty good, yeah? Yeah, does everybody's look like that on your calculator screen? Okay. All right, I'm going to hit y equals, and I'm going to turn this off. So I'm going to turn it off by I go onto the equal sign. Okay, you just arrow onto it and you select it. You hit enter on top of it, and it turns the graph off. So like if I graph now, it's not going to show up because I want to graph the other one without this one interfering. So I'm going to do stat calc, and we'll do cubic reg number 6. But I want to make sure that I put it into the second function so that I don't write on top of the y1 that I'm trying to sort of save in case it ends up being the best one. So here's cubic reg y2. This plugs it into the cubic, or plugs the cubic model into the second equation for y2. And if I hit graph, I will see a graph for this one. And it also looks pretty good, doesn't it? Okay, so they both look great. So when 2 functions fit the data equally well, how do we decide? We base it on the end behavior. So this graph, what is the end behavior doing on this graph? And I don't mean the dots, I mean the equation that's connecting them. What is happening toward the end of this?
Towards both ends or
Just as we go on and further in time, toward the right side. It's decreasing. Are her cumulative number of tickets sold going to decrease? Not unless people call and cancel, right? They've already been purchased. So that isn't possible. What about the logistic model? What is its end behavior going to be? It's increasing and it kind of levels off. Do we expect that to happen eventually on this cruise? Yeah, because she's going to sell all the tickets, right? I mean, that's the idea, is that at some point there's no more tickets to be sold. It has to level off. So the equation that we're going to choose is the logistic equation because both of them fit equally well, or at least approximately, equally well. And this one has a better end behavior for it. The equation is written right here. It looks a little bit funny on my screen. Yours might look different depending on your calculator version you're looking at. So if you want to recalculate it so that it puts it into a different screen and looks prettier, you could do that too. So maybe I'll just do that just for the sake of having done it. And then we'll write this equation down. All right, so the 5,000.084 will be the C value on top. Oh, we need a name for our function. These are tickets sold, so I'm going to call it capital T of X. I have 5,000.084 on the numerator. In the denominator, there's a 1 plus, right? The A value, which is 98.973. E to the exponent negative B. So the B value is 34995. And if I use that to 3 decimal places, then this third 9 would get rounded up by this 9, right? And we'd end up with 350. Yes?
All of my numbers are slightly different.
Okay, let me come take a
Very
look.
slightly different.
Negative point, oops, 350x. I'll come back and finish. Usually when the numbers are slightly off, Cole, it's because one of your data points is slightly off. I mean, even by a million, just like one value. Let's double check. Yeah, it's crazy that one little value can make everything off so slight. Yeah, okay. Now, not many of you stopped at this point on the test, but there are still a couple of you who are stopping at this point in creating a model. This model's not quite done. What is it missing? All the units, all the language around it, right? So we write the output units first. So based on this model, what is the output? What's coming out of this function? Tickets sold. So we're going to write down that this is tickets sold. After I put the output, I need to put how the input is being determined. What is the input on this?
Your X is weeks.
The weeks, a little bit more. Probably something like the weeks after she begins selling tickets. Because weeks is a little bit weak. Yeah? It's hard to know exactly what that means. For example, some of you put just minutes. We had the buffet question. This buffet question was the last one I graded, I think, before I left my office. That's why it's on my mind. And some of you just put minutes. Well, minutes what? Well, it's minutes since the buffet started or the party started, right? So this would be, what did I say? Oh, wrong screen. X weeks after she starts selling tickets. I actually was just thinking that myself. I think that would be a good idea. So let's actually change where it says tickets sold. And we'll put cumulative tickets sold. Just to be very clear. If you don't put it, it's not a huge deal. But I think this is clear. Cumulative tickets sold X weeks after she starts selling tickets. There's one more thing to do, right? The input interval. So I believe it started with 1. Where did it stop? 25. So 1 is less than or equal to X is less than or equal to 25. Okay. I like this example because we can keep going and we can actually keep talking about what we would do next if we actually were starting with an equation instead of starting with a data table. So first of all, we started with a verbal description, right? And we used a verbal description to calculate these quantities and interpret them. Our second problem, this one, started with a table. So you had a table of values you were looking at to make your calculations, and we didn't do the interpretation on this one, although we could have, right? Sure. What we're about to do on part D is we're about to take an equation, and this one is an equation we created, but it doesn't really matter. If you were given an equation that was, on your paper to begin with, you would do the same thing. All right? So what we're going to do is we're going to calculate using the model, the change, the percent change, and the average rate of change over the same time interval that we did from the earlier part, 4 weeks to 16 weeks. Okay? So we'll start with change. So when we do change, we're finding, and I called my function capital T, so whatever you used your function name to be, this is what you'll write here. And you're going to put the second, or the newer, input value. What is the newer input value for the interval we're looking at? Week 16. So this is T of 16 minus T of my earlier value, which was 4. I want T of 16 minus T of 4. I'm not using the table. I already did that. I'm supposed to be using the equation that I've been given or that I created. In this case, I created it. So if you'll take a calculator, and if you still have it stored in Y1, hopefully you do. If not, you need to get there. So mine is in Y1 here. And we're going to use this inside of the, well, you could do it inside of the table. That's what we've been doing, with all of our values before. And you could write down 16 and 4, and you could take these two numbers and you could subtract them somewhere else, correct? But wouldn't it be nice if you could do all of that in the same screen and you didn't have to write any of those numbers down? Or like take a picture of them with your phone or something like that, and then it would be nice. So I'm going to show you how to do that. Go back to your regular screen. You can have this listed here, or you can clear it off, doesn't matter. Our goal is to find T of 16 minus T of 4, right? Okay, you all know how to pull up Y1 in the vars function, right? You hit vars, yvars, function, Y1. Pull it up. And then next to it, put a parenthesis with the 16 and close it. And then minus vars, yvars, function, Y1. A parenthesis with a 4 and close it. And if I hit enter, it's going to subtract those two output values for me. Yeah, and the reason it's almost the same answer is because it fit our equation so well, right? So we do expect our answers to be very close to what we originally had from our table. So this is 3462.902149, but the units on this answer for change are what? Tickets. So if you write down 3,462.902149, I'm not going to like it. Why?
You can't sell like 0.9 of it.
You cannot sell 0.9 of a ticket. Doesn't make sense. Some of you told me you had 0.1 of a roll left over. Also not quite what we're looking for, right? Yeah. Okay. So take a look here. We're going to write this down as what? What would this be if we rounded this?
63.
Yes, we do 63. Okay, so we're going to write down 3463 tickets. Okay, our next one we're supposed to find is percent change. So the percent change has the same numerator as the original value we found for change, T16 minus T4, over what? Yeah, whatever your function name was, f of 4, T of 4, whatever you have. And then what? Times 100. Okay, so we're going to take this sort of model, how it's written here, and we're going to plug this into the calculator. So let me show you how it looks when you do that. If you still have the value on your screen, I hope you do, exactly as it's written. That's your easiest option because right here you can hit division, and it takes the previous answer. And that previous answer will then be divided by, and you can do vars, yvars, function y1, of 4. You can even hit times 100 right here, and it will do it with order of operations correctly. It will do the division first, and then it will do the multiplication second. I know, and there's your percentage, 1759.886%. Tell me what I do for average rate of change.
T16 minus T4.
Okay, so same numerator, right, Luke?
Yeah.
Okay, T16 minus T4.
3660 minus 197.
No, that's a good guess.
16 minus 4.
It's the 16 minus 4, the x values instead of the y values. So 16 minus 4 or 12. Okay, so let me show you over here what you can do. This wouldn't be too bad on this one. We could go back and we could type something in by hand, but I don't really want to show you that because I know you how to do that. I want to show you a cool calculator trick. What we really want is we really want this first line that's on my calculator to be the numerator of my next value, correct? And yes, I could enter by hand 3462.902149. I could do that. Agreed? Sure. But I'd like for you to try something different. I would like for you to hit second and hit the enter button. And notice, I'm going to zoom out this a little bit. And notice what it did was it pulled up the previous line of text. Okay, that's cool, but if you do it again, it'll go back up one more. So you don't have to type it in again. You can just do second enter twice, pulls it back up. You hit enter. Oops, don't hit plus. Hit enter. You can divide it by, if you weren't wanting to do the subtraction or if it were messier, you could actually put a parenthesis and do 16 minus 4. This one's simple enough. I'm sure you know that that's 12 and you could hit just 12 and go with it. But here's what we have. 288.575.
On mine, if you just toggle up to the one you want to press enter, it'll break down the clock.
Cool. You have to show me that. I wonder if
When I close
it doesn't go up. See? Yeah, that's not a feature on the TI-83s. I have an 84 in my office. I'll have to try that. Yes?
So for your answer, would you just go like 288 or 289?
It's a good question. So what are the units on this one? What are the units on average rate of change? Tickets sold per week. And the kicker with this one, I know it feels like, well, that's a number of tickets, and it is, but it's an average over time, and it's perfectly appropriate to have an average that includes decimal points. So for this one, it's Lucas, right? For this one, yeah, Lucas? Yeah, okay, I was making sure I had your name right. I'm trying. So for this one, you actually are going to include the decimal points because it's an average. So it's 288 point, what did I have? 575? Tickets, whoops, that was not spelled right. Let's try that again. Tickets per week. Okay, so we found the three quantities. We can compare them because we did it from the data table earlier. Typically speaking, they're not going to ask you to do the quantities from the table and the quantities from from an equation. But we can compare them. We can see that they're giving us very close values. And the closer that the curve matches our scatter plot, the better it's going to approximate it. E is a great question, though. Which answers are more accurate? Those found using the table or those found using the model? You seem pretty sure, Lucas. Why?
Because that's like your actual values.
Yeah, you're exactly right. So the table should be more accurate because those are the real values. You see, we went through this sort of in-between step where we approximated it by an equation, right? But the equation itself is an approximation, agreed? So if I use an approximation to calculate something, it's going to be less accurate than if I use the actual values. So the correct answer is actually the table because they are the exact values. Okay, so we have found change 4 ways so far. Verbal description, data table, equation, and the last one is a graph. So we're going to do them by a graph. And this will be an approximation. The first thing you need to do is to fix the graph that's on your paper because it all shifted somehow. And it's really weird because this printout that I have, it's not shifted on. But your printout, once I saw the PDF of it, it was. So just shift these over. The first hash mark on the x-axis is 1990. Skip one, and then you've got 1910. Skip one, 1920. Skip one, 1930. Okay? Does yours look right? It does? Does anybody's look wrong? I saw it this morning and it looked wrong.
Oh, no.
Wonderful. So half of them are right and half of them are wrong. That was fun. Is it wrong? Nope, yours looks great.
Pretty.
I printed mine out like.
Yeah, pretty much like before.
If you print it out today, you're probably good to go because I fixed it this morning. You printed out the ways ago. Did you print yours this morning? That's why. Okay, good to know. All right, so just fix it so that it's lined up properly. Everybody good with that? Okay, cool. Okay, so here we have a graph, not a table, a graph. The accompanying graph models the number of states associated with the National PTA organization from 1895 through 1931. And I don't have my question on this page because I don't have space to actually do all the parts to it, so here's the question. It says to find the change, percent change, and average rate of change in the membership from 1905 to 1915. So we're going to find all three quantities from 1905 to 1915, and when we do this, we're going to have to approximate, right? I mean, that's just that's our only choice. So taking a look at our table, 1905 is the hash mark that's not marked right here. And what we want to do is we want to, if you will, go up from this hash mark and figure out approximately what the y value looks like it should be at that particular point in time. So what does the y value appear to be right here? 5 or close to it. 4 or 5 depending on your value. So we'll say 5 because you guys chose that it was a 5. So we'll say that this is at 5. The other value that it gave us was 1915. That's this one. So if I take 1915 and I go up from here, and if I go over, I'm awfully close to 20. Is 20 okay with you guys to use?
Yes.
Okay. So this one's at approximately 20. So these are the output values I'm going to use, 20 and 5. So to start with, we're going to find the change. Okay, so what do I do to find change? New minus old. What's the newer value here? 20. And the older value? 5. 20 minus 5 is? 15. That's like first grade stuff, right? Yeah, definitely. 15 what? States. Remember, this was a number of states. So this is 15 states. Okay, percent change. So the numerator should look just like what I just did, right? Don't reinvent the wheel. 20 minus 5. What's in the denominator? 5. It's always the second value. And then what do we do? Times 100. So you know your numerator is 15. What is 15 divided by 5? 3. And 3 times 100 would be 300. And the units? Percent. And the last one, average rate of change. Same numerator, 20 minus 5. What's my denominator?
19.
Somebody was saying it. Go ahead.
1950.
Yeah, 1915 minus 1905. So the numerator is still 15. What's the denominator? 10. And what is 10 divided by 15? I said it wrong. Yes, thank you. 15 divided by 10. Don't make this hard, guys.
3 over 2 or
1.5. That's what it really is. Divide by 10 just moves decimal points. 1.5 what? States per year. The numerator is states. The denominator is years. And it should make sense to you to say it's 1.5 states per year. That's okay, right? What that means is over the course of 2 years, we have about 3 states joining, correct? Yeah, that's all right. Okay, so this is from 1905 to 1915. This one says 1920 to 1925. But the process should be the same. We just have to go collect the values that go with them, correct? So let's take a look. Oops, one more. 1920, that's actually marked down here. And 1925 is my next one. So 1920 and up, 1905 and up, Where do you approximately think you are on your curve at those values? How about the 1920 value? What's that look like? 40? And the other one we said about 45. That sounds reasonable. So as we're calculating, first we're doing change. What do I do? 45 minus 40. Let me pause right here and make a comment. I know you can do 45 minus 40 in your head without writing it down. I know that. Please write it down, because if you get an answer that's substantially different, I might be able to figure out where you went wrong, and we can fix the error in your thinking instead of just saying it's wrong and you get 0 points. Is that okay? So write down the 45 minus 40 for me before you write down that this is 5 states. Did someone have a question?
Yeah, I was gonna ask, like, for percent change and average rate of change,
Mm-hmm.
do you have to write out 45 minus 40 in the numerator, or can we just?
You could write this, yeah, you could write the 5 in the numerator. The thing that I do like about writing the other one, just let me show you this for percent change, is that if you write this part down, I'm kind of a visual person, and I like seeing that the 40s match. That's just me. You don't have to do that, but that's something that I kind of like to be able to see, that makes sure that I'm dividing by the right quantity. So yeah, but you could put the 5 in the numerator here and continue. That'd be okay. Okay, so 45 minus 40 is 5. 5 divided by 40, and then times 100. Probably need a calculator for that one. What does that give you? 12.5%. So just so that you're aware, our answers that we're getting right now don't match my paper. Any idea why that might be? I estimated slightly differently, right? So it's okay, especially when you're looking at an approximation from a graph, if your answers in the back of the book's answers and your neighbor's answers are all 3 different. They should still be fairly close though, right? If they're substantially different, there's probably an error somewhere, but otherwise you're probably good to go. All right, last one, average rate of change. Same numerator, either write down the 5 or the 45 minus 40. What's your denominator on this one? It's 5. It's actually 1925 minus 1920.
Do we have to show that?
No, but I need at least a 5 over a 5 somewhere.
Yeah.
Yeah, that's okay. Yeah. And this would be 1 what? 1 state per year. Now, go back to the graph for me before you start packing up. This answer was 1.5 states per year, and this answer is 1 state per year. Can you justify for me why that makes sense on this graph? Okay, so we don't exactly have slope because it's not a line, the rate of change, but why from the graph? Yeah, so I think maybe the word you might be wanting is the word steeper. It's much steeper right in here. There's more states that are joining because there are more states to still join, right? Over here, it's starting to level off. It makes sense that it's actually slowing down because there are fewer states left that haven't joined the particular organization. All right, that's it for today.